another maybe a few seconds.
Yes, sure.
Good. Yeah, and Professor Sean, you'll be starting the orientation, right?
Yes,
Uh,
I
I,
will.
oh,
Yeah.
okay. I will be having my camera and mic turned off, but
Mm-hmm.
I'm just trying to figure out the videos to be played on time. But otherwise, the other video is already in my laptop and can be played on time. You just have to call the speaker. So I'll just try figuring out the other video alone.
All right. That's great.
Thank you, Professor Sean. Yeah,
Thank you.
you're welcome.
Hello, everybody. So this is session uh, 2B, electrochemical systems. So we're happy to have electrochemical desalination. So we have 5 speakers today. And then my name is Ho Kyung Sean from University of Technology Sydney. Happy to chair this session. And I have co-chair Professor Daiwei Liang. Please, can you please introduce yourself?
Yep. Good morning, everybody. Thank you, the chair, Professor Hokyo Sean. I'm David Liang from Beihang University in Beijing, China, and I'll be the co-chair for this session 2B. Okay.
Yep. So first, we have three first speakers. They will have live presentations, and then last 2 speakers, they recorded their video. So we will just show video and then have a Q&A session. So please, Daiwei Liang, so can you please introduce the first speakers?
Okay. The first speaker will be Hao Jiang. I don't know how to call you. Is it doctor or professor? I don't know. Anyway, Miss Jiang will give us a presentation on the topic of development of novel composite electrode to selectively remove phosphate for capacitive deionization. Uh, Jiang is from Tongji University. Okay, now the time is yours.
Okay, thank you. Hello, professors. I'm a PhD candidate from Tongji University. My name is Hao Zhang. It's my honor to be with you to communicate academic ideas. Today, I would like to share some of my research progresses on development of novel composite electrodes to selectively remove phosphate for capacitive desalination. My presentation is structured in the following way. The biogeochemical cycle of phosphorus lacks a gaseous atmospheric component to assist with cyclic replenishment of soils. Phosphorus flows now lasting the anthropogenic cycle. This will involve new technologies targeting liquids and solids, including erosion and drainage, animal waste, municipal waste, and industrial waste. Among them, with the rapid development of population and social economy, wastewater from human activities is one environmental problem of all over the world. Phosphorus enrichment in wastewater discharge lead to the deterioration of aquatic ecosystem and the loss of water supply resources utilization. Therefore, the phosphate emission standard has become more and more strict, and the primary standard, 0.5 mg per liter, and secondary standard, 1 mg per liter, have been formulated. At present, phosphorus removal and recovery technologies are mainly divided into physical, chemical, and biological methods. Traditionally, biological phosphorus removal had been widely used in wastewater treatment. Enhanced biological phosphorus removal had high efficiency. However, its stability is poor, and the removal of phosphorus by sludge pyrolysis brings new problems. So a large number of new technologies have emerged, such as electrochemistry, adsorption, and membrane separation, which can absorb phosphates quickly and efficiently. However, these processes gradually have some problems, such as complex operation, high energy consumption, and high cost, and so on. In recent years, capacitive deionization, a new desalination technology, has been applied to sewage treatment. It's considered to be an ideal process for simultaneous removal of salt and nutrients. It uses the conductivity and adsorption of carbon electrodes to make the positive and negative ions in the solution move to the electrodes at both ends. And then they are stored in the electric double layer to form an intermediate deionization area. In this study, an organic-inorganic composite material was successfully synthesized by terephthalic acid into zinc zirconium layer double hydroxide. To maintain the traditional properties of porous electron material, we designed and prepared carbon nanotube composite LDH electrode. Here you can see the two figures which show you the capacitive deionization device and the process of material preparation. First, the materials were analyzed by SEM, SRD, and BET. In these figures, we can see that zinc zirconium LDH small particles sharp through the narrow pores and surface of CNT to form a huge honeycomb. And EDS spectrum also show the high dispersion of zinc and zirconium elements. BET analysis stated clearly that zinc zirconium LDH dope CNT had a large number of micropores and macropores, and a specific surface area was 294.2 square meters per gram, which was higher than that of CNT and zinc zirconium LDH. Then, using the electrochemical workstation, we obtain the CV curve and Nyquist impedance spectrum. The key results are listed in this table. The capacitance of zinc zirconium LDH dope CNT electrode was between CNT and zinc zirconium LDH electrode. And although the charge transfer resistance of composite electrode was larger than that of CNT, it gave a lower solution resistance, so that the electrode maintained a lower total impedance. The following is the impact test of CDI operating conditions. We studied the effects of initial phosphate concentration, pH, and voltage. For composite electrodes, the picture shows you when the concentration was less than 10 milligram per liter, the final concentration was less than 0.5 milligram per liter within 5 hours in a wide range of pH 3 to 10. This is because zinc and zirconium can be combined with phosphate through the ligand exchange, and the existence of carboxyl group increase the adsorption site of phosphate. Besides, when the pH was in the range of 3 to 8, pH less than 0 isoelectric point, the electric surface still had more positive charges, so the phosphate removal efficiency was high. And when the pH was in the range of 8 to 10, the the carboxyl group was completely deprotonated, which can be used as a hydrogen bond receptor and can only absorb phosphate. In figure E and F, we can see that the higher the voltage, the higher the phosphate removal efficiency. And with the increase of voltage, the formed electric double layer gradually thickened. By calculating and fitting the above measured data, we obtain the absorption kinetic curve under different initial concentrations and voltage. The results show that the absorption of phosphate on the 3 electrodes followed the pseudo-second order kinetic model. It indicated that with the increase of initial concentration, the absorption capacitive accumulated more and more. In these figures, it was observed that the higher the voltage, the faster the absorption rate, and the faster the absorption equilibrium was reached. Higher voltage provides stronger driving force for ions, and a thicker electric double layer was formed on the electrode surface to accommodate more phosphate ions. Next, we further study the absorption process of the electrode and propose a possible absorption mechanism. In the left figure, the presence of distinguished sharp peaks of zirconium 3D, zinc 2P, and oxygen 1s in the SPS first gas spectrum. And in the right figure, a new peak of phosphorus 2P was observed on the absorbed electrodes. Besides, after phosphate absorption, the binding energies of zirconium, zinc, and carbon decrease and increase to a certain extent. This is because of the ionosphere complexation and coordination exchange, which change the density of electron clouds around atoms, resulting in the increase or decrease of binding energy. These mechanisms mainly included phosphate was absorbed to the electrode by electrostatic attraction, the hydrogen phosphate ion and hydrogen phosphate ion on zirconia via the ligand exchange and ionosphere complexing mechanism, forming zirconium, oxygen, phosphorus ionosphere complexes. The phosphate ions can exchange with these OH groups and complexing with zinc on the surface. The deprotonated carboxyl group formed hydrogen bonds with phosphorus oxygen double bond and phosphorus oxygen single bond. Finally, the selectivity and economy of the electrodes are discussed. There are many types of ionides in real sewage. These pictures show the effects of different coexisting ions on phosphate absorption. And we can see chloride ion, nitrate ion, and sulfate ion had a slight impact on phosphate absorption. And the final concentration was less than 0.5 mg per liter. But the existence of bicarbonate ion inhibited the absorption of phosphate to a certain extent. In order to evaluate the stability of composite electrodes, we carry out 10 absorption release experiments. The results show that in the first 4 cycles, the phosphate concentration was lower than 0.5 mg per liter, and in the 10th cycle, it was less than 1 mg per liter. Moreover, in low concentration phosphate treatment, the operating cost of this study was only 1/16 of that of chemical phosphate removal. In short, a novel electrode, zinc zirconium and digital CNT electrode with high selective for phosphate adsorption was successfully prepared. It showed greater adsorption capacity for low concentration phosphate in a wide range of pH, with a final concentration as low as 0.5 mg per liter. This study reported the potential of the electrode in the practical application of removing phosphate, and further efforts should be made to maximize the advantages of this work. Finally, I'd like to make some acknowledgements. First, I would like to thank Professor Zhao Wu, Zhiwei Wang, and Qiaoying Wang for their guidance. Finally, I would also like to thank the National Key Research and Development Program China, National Natural Science Foundation of China, and the Shanghai Rising Star Program for the financial support of this study. Thank you.
Okay, thanks, Hao Jiang.
Yeah, thank you.
The time is good, so we have 5 minutes for the questions. Any questions? Okay, I have some. All right. So this composite electrode is specific for phosphate removal. So the zinc, zirconium, and is a carboxylated group on the electrode. But what is the electrode for cathode? That means the other side of the electrode. What is the material of the
In this study, we used the carbon nanotube and zinc zirconium LDH electrode as a comparison. We study the phosphate concentration and pH and coinciding ions for the selectivity phosphate removal efficiency.
Yes, I understand. But the electrode you prepared is specific for phosphate. I mean, what the other side of the electrode, the cathode part?
It's carbon electrode.
Carbon electrode.
Use carbon electrode. Yeah.
So you use a hybrid system.
Yeah.
That means the anode and cathode are the same, right? What about the long-term stability? Long-term stability of this CPI. Is it still good after several cycles or tens of cycles?
Is
you know my question?
10 cycles. 10 cycle. The final concentration. In this picture, the final concentration at 1 milligram per liter.
Yes.
So
in 10 cycles, it's still stable.
Yeah.
What about the stability after 10 seconds? Have you
The
investigated?
in the next study we can we can change this work.
Okay, I see.
Thank you. Thank you.
Any other questions? I think the audience could also ask the questions as well. Here it comes. One question from our audience asked, are the cathode and the anode the same? I think Hao Jiang has already answered the question just now. The cathode is just simple carbon, right? Activity carbon.
It's carbon electrodes. We combine the carbon electrode and zinc zirconium and digital CNT electrode to communicate 如何 combine the capacitive deionization device.
But anyways, I think you could also answer the question after the talk in the chat group. Okay, let's